In this video series, I program a robot from scratch in C, and while the end goal is obviously to have my code run on this robot, initially I'm using this development board which has the same microcontroller on it, and I'm doing this to make the videos more isolated, but also to show you that you can write a lot of code before moving on to the actual hardware, which can be useful in a real project cycle. But because of this, I end up with having to support two targets, the development board and the robot. And in the previous video, I added preprocessor directives to distinguish between the two at compile time. This resulted in me having to manually edit a file every time I want to switch between the two targets. This is annoying and ugly, so in this video I'm going to improve on this in two ways. First, I'm going to improve it at compile time. I'm going to make it possible to pass the target as an argument to my build system make, or in other words, I'm going to make it so that I can write make and sumo to target the actual robot and make Launchpad to target the development board. And as a bonus, this will let me add both build targets to my SIA system. Secondly, I'm going to implement a way to distinguish between the two targets at runtime. This will serve as a sanity check to prevent me from accidentally running code on the wrong target. And the way I'm going to do this is similar to how you would go about detecting different board revisions at runtime, which is often necessary in a real project cycle when there are multiple hardware revisions in use at the same time. As usual, I begin with a new local Git branch, this time named feature hardware versioning. Then I open the header file io.h, which is the file I currently have to hand edit every time I want to change targets. So at the moment I have to write define Launchpad to build for the development board and define ensumo to build the code for the robot. And since I'm going to replace this with an argument passed to make, I remove this line, which as expected makes the compilation fail for now. So I then jump over to modify the make file. In the make file, I first add a variable to hold the define. This variable takes the value from an argument named hw, which I'm going to pass to make on the command line. I prefix this with capital D, since that's how you add defines as a flag to the linker and compiler in the GCC toolchain. I then add this variable as part of the compiler and linker flags and confirm that it works by running make Launchpad and make ensumo. Next, I edit the target variable to name the final executable according to the target I'm building. I mean, instead of always ending up with the same name ensumo. I introduce a new variable for this named target name, and I set this at the top of the make file by checking the arguments passed to make. I write this in a way as to make the argument a requirement and report an error when it's missing. I also remove the bindir variable here since I'm not using it anymore. I then test it on the command line by executing make w equals launchpad and see that it creates an executable named launchpad. And similarly for the robot, I run make w equals ensumo and check that that also creates an executable named ensumo, and then that I also get an error if I don't supply the argument at all. So it works as expected. One small problem, however, is that I have a couple of rules that shouldn't require the HW argument. For example, clean. I don't want to get an error when writing make clean without argument, since the clean rule doesn't really depend on any particular target. It should remove the build directory regardless. The best way I could think of to get around this was to add an extra check at the top to exclude the clean rule. I also do the same for the CPP check and format rules. With all of this fixed, I could then also add the two build targets as two separate steps in my CI workflow, which ensures that every commit compiles for both targets before they can be merged. Then I commit the changes, push the branch to GitHub, and open a pull request. All checks passed, but I didn't merge it at this time because I wanted to use the same branch throughout this video. So what I had now was a way to easily switch between the two targets at compile time. This was definitely an improvement from before, but it doesn't actually prevent me from accidentally flashing the wrong software to the wrong hardware, which is something I could easily end up doing by mistake, since my computer and debugger don't know which target I am flashing to. The microcontroller appears the same regardless if I'm flashing to the development board or the robot. While this is unlikely to cause any serious issues in this case, more than wasting my time, it's bad practice to run software on the wrong hardware, since there is always a risk that it might damage the hardware. So for good practice, I decided to add an extra check to prevent this from happening. And I can do this check by adding a piece of code that detects the hardware type at startup and that hangs if it detects a mismatch. But a problem with this is that it requires me to have a way to programmatically detect which hardware the code is currently running on. And this is a problem because the microcontroller on the robot and the development board are practically the same. The only difference, as far as I know, is the pin count, 24 versus 16 configurable IO pins. Initially, I still thought that I could maybe use this pin difference to distinguish between them by comparing the values in the port 3 registers. But it turns out that there is no internal difference between these registers. I read the same value on both targets at startup, so I couldn't use that as a way to distinguish them. As such, I saw no other way but to introduce a difference myself by patching my PCB. And looking closer at the PCB, the simplest change that I could come up with was to add a pull-up resistor to one of my unused pins, and pin 3.4 seemed like the best choice. As a side note, soldering pull-up and pull-down resistors to GPIOs is a common technique for distinguishing between different hardware and board revisions, since the combination of resistors form a binary number. For example, with one GPIO or resistor you can represent two versions, with 2 GPIOs 4 versions, and with 3 GPIOs 8 versions, and so on. In my case, I get away with only sacrificing a single GPIO since I only need to distinguish between 2 different versions. So having this figured out, I went ahead and soldered an external pull-up resistor onto my PCB. First, I unscrewed the top plate from my robot. I'm using a large/weak pull-up resistor here, one rated at 100k ohms, to minimize current consumption. I solder it between the 3.3 voltage and pin 3.4. And at this moment I thanked myself that I had made these lines easily accessible on my PCB. And note, another approach you can take if you don't have a lot of GPIOs to spare is to use a single ADC pin and to solder a resistor network giving a distinct voltage, because then you can map this voltage to a corresponding version number in your code. I'm not doing that here, but I just wanted to mention it as a tip, and I will leave a couple of links in the description for more details about this. Not the nicest soldering perhaps. I would have preferred soldering it on the rear side of my PCB, but the tiny Molex connectors makes the PCB a nightmare to unmount. So I took the easy way out this time. With the pull down soldered, I could get back to implementing the code to detect it. To do this, I defined an enum inside io.c along with a function called detect hardware type. And inside this function, I configured the pin as input using the raw register defines given by TI. I would have preferred using my own IO functions that I created in my last video, but port 3 is not part of the enums when building for the Launchpad, so it wouldn't compile if I did. I then read the input level, and if it's high, I know there is an external pull-up resistor, which means it's the robot, and if not, I know it's the Launchpad. As always, I also like to add some clarifying comments. I then call this function at top of io_init before the pins are initialized. I compare the return value, and if there is a mismatch, I hang in an endless while loop, something which I'm going to replace with an assert in my next video. To test this function, I decided to run the test blink LED function that I added in a previous video and to run it on both targets. So I uncommented this test function inside main.c. I began by testing it on the robot. I used the same debugger for both targets, the one included on the development board, because I have no standalone debugger for MSP430, so this is the way I have to do it. And for the robot, I have to connect the debugger on the development board via 3 jumper wires. So to verify that it works, I first build and flash the correct software to the robot and see that the LED blinks, as it should, because then the test LED blink function should be running. Then I build and flash the incorrect software and verify that the LED stopped blinking, since then the code should be stuck inside the endless while loop. Then I do the same for the Launchpad. First the right software, seeing the LED blink. and then the wrong software seeing the LED not blink. One annoying thing I noticed while doing this is that I have to clean the build folder between switching the build target, because otherwise make doesn't rebuild the new target since I don't modify any file. I just change the argument. To get around this, I modify the build_dir variable inside my makefile to also create a subdirectory based on the target name, which in turn gives me two separate directories, one for each target under the build directory. After that, I was satisfied, so I formatted, CPP checked, and committed my code. I pushed it to the same pull request on GitHub, and see I passed. Lastly, I wanted to fix some typos that I introduced in my previous video. Most importantly, to enable the resistor on one of the pins. I then committed and pushed this as well. It passed, and finally I merged the pull request. That's it for today. Hardware versioning is another one of those topics that becomes more relevant as you work on actual embedded systems projects, which usually spans many board revisions. On a toy project like this, it's more a nice to have, but regardless, I think it's an important enough of a topic to be included in this video series. Anyway, see you next time.